Okay, so welcome to geometry. Hi. All right, oh, how's the glare there? I might have to close the shade. Hopefully that's marginally better. Right, so, we're going to start by just talking about what this course is about and some basic logistical points. And then we're going to talk a little bit about a bit of a historical background. And then after that, we'll talk about some formal definitions. And I was explaining before class began to the students who are in class, typically I'm going to, at some point during most lectures, assign some homework problems. And then at the beginning of each lecture, we'll kind of go through them together. We'll go through some of them together to illustrate the main points. Okay, I'm not going to collect any homework. But we should go through those exercises together, so we have a better comprehensive understanding of what's going on. Okay, so, right, before I get too far in and forget to say this, there's a survey on Canvas that just asks for your preference for when you would like to see office hours happen and what time zone you're in typically, for those of you who may not be in the Boston time zone, just so I can coordinate the tests better. And then just a little, I would like to know a little bit about everybody's background in their studies, in their pursuit of mathematics, just so I can kind of tailor the course a little better. So a lot of you already completed that, but if you haven't, please just take a couple minutes. It shouldn't take more than like 5 minutes to go through. Okay? So, let us see. What is this course all about? Well, it's in a kind of unique place in terms of where it fits in the undergraduate mathematics curriculum. If you read the description on the course catalog, it says something along the lines of that it's a class designed to prepare people to take group theory, or perhaps differential geometry. Okay, and that in large part is a huge function of this class. But I also think that there's a certain value it adds in the historical description. This textbook, by the way, the textbook that we'll be using, George E. Martin Transformation Theory, this is on the syllabus. By the way, the syllabus is linked on Canvas, so please take a look at that. There's a week-by-week schedule of what we'll be doing. But I think this textbook does a really good job of providing historical context and kind of I guess it kind of pushes abstraction to the back end of what is necessary, right? The history and the particular application of the study of transformation groups allows you to get a kind of concrete view on group theory. So I think there's value in this course, even if you are quite familiar with group theory already. It may seem a little easy at the beginning, but I think that will pay off for the perspective that's provided by this treatment. Okay? So, logistics. I foolishly didn't write this down in my notes. Well, there'll be 4 tests, which are for a total of 60% of your grade, the lowest score dropped. Okay, so as I said, no handed-in homework. That's just something that we're going to do together to get perspective. But yeah, so your lowest score will be dropped. And then there's a final exam, which will be 40% or 50%, whichever gives you a higher grade. Okay, and if it so happens that counting the final for 50% gives you a higher grade, the 4 tests will be scaled accordingly to make up the percentage. Okay, so yeah. Did I already explain how the homework will work? Yeah, I said that. We'll do it together. A consequence of that is that this lecture might run a little short. It's because I didn't assign you any homework beforehand. I feel like that would be unfair. Okay? So, I also received a lot of questions about the lecture being recorded or not. And they will be recorded through the Zoom link on Canvas. You can go look at the cloud recordings. I'm also going to upload all the recordings to my YouTube channel. So I'll make a playlist for this course. If for whatever reason, I have had some Zoom Canvas malfunctions in the past. So you'll always have YouTube as a backup as well. Okay? Good. Good. Oh, the other thing I wanted to say was, it nearly slipped my mind yesterday that it was Mother's Day yesterday. So it didn't exactly slip my mind, but it nearly did. And I just wanted to say, one day isn't enough to show appreciation to mothers. So I wanted to say I wouldn't be here today without my mother. Okay? All right. So are there any questions on logistics or mothers? No? Oh, another thing is, I know some of you may not be comfortable with speaking up over Zoom. And I've learned this over my time at Northeastern during the pandemic, that I try my best to constantly look at the chat for questions. But if you feel comfortable, it's really helpful to me, and I think everybody, if you unmute yourself and ask your question aloud. Please interrupt me whenever, if something doesn't make sense, or if you want to answer a question that I pose. It would be ideal if you unmute yourself, but I understand if you don't want to. That's fine. Okay. So, I think we're ready to start discussing mathematics, or at least partly the history of mathematics. Okay? So, here's a fact. There are only 17 mathematically distinct wallpaper patterns. Okay. This is a bold claim, a seemingly highly unlikely theorem. But really I haven't stated a theorem here. I haven't made precise what I mean by mathematically distinct, right? So that's going to be our central goal. Is going to be to get to the point where we built the machinery to prove this. Okay? And then we'll fill in the rest of the term after we do that with whatever interesting material fits everybody's common denominator. Okay? So, right. So, let me just say, this was known to Spanish Moors in the 15th century. However, not known to Euclid. And when I say that, what I mean is, i.e., there is no such mention, no such result in Elements, which is circa 300 BC. Okay, why do I make a point of saying this? It's because when you think of geometry, when you think of, again, we haven't said what mathematically distinct means, but this is, your intuition probably tells you that this is a geometric property of some pattern classification. So it's kind of remarkable that usually when we think of geometry, the Greeks knew everything. Not so. Not so. And this is because, well, what happens over time is that different viewpoints and methodologies are developed to explain the same phenomenon. Right? And I think, especially as 21st century mathematicians, it's our job to understand how these different viewpoints intermesh and how they can be made useful to one another, to mutually expand one another. Okay. So, that is to say, in this course in particular, what we want to do is we want to take the classical view of Euclidean geometry and slightly change our viewpoint when we look at Euclidean geometry through the lens of transformation geometry. Okay, so we want to see classical Euclidean geometry through the lens of something we'll call transformation geometry. Okay. The study of collections of transformations of the plane. Now, of course, if you're familiar with the elements, you know that it's almost entirely plane geometry. So transformation geometry is a slightly different set of tools. You can use it to study higher dimensional spaces other than the plane. But we'll primarily be concerned with the plane. We may well get to some spatial aspects of transformation geometry, But that just depends how we move. Okay? So, just want to take a quick aside here. Collections of transformations of the plane. This is kind of this is one of the earliest incarnations of a very modern viewpoint of mathematics, where you learn more about an object by studying the maps of that object into itself. Okay? So for those of you that are interested, this is like a core tenet of the philosophy of category theory. Okay? That's my area of research, so I feel like I would be remiss to not say so. But that's not going to be a focus of our course, other than for the plane, and possibly space. Okay? So, let us make some definitions. I've been quite vague so far. Okay, first of all, a mapping F going from R2 to R2 on the set of points in the plane. P, an element of R2. Okay, I'm going to introduce notation as we go here, just in case people aren't totally comfortable with this. That's fine, but I think we'll all pick it up as we go. My R2, this is my standard notation for the plane, and we'll talk about how this is actually a model of the Euclidean plane. This is a particular model, but it's the model that we're mainly concerned with. Here I have a lowercase epsilon, which means that P, my point, is an element of the plane. Okay? Is a function. Right? That is to say, its entire domain is all of the plane. Every point goes to some point in the plane. Okay? So, instead of all mappings of the plane, it's too large to be interesting. We have to pare it down to get something interesting. That's why we want to make a definition of what a transformation is. Okay? So, a mapping is onto or equally well, you could say surjective if for every point, what was my notation here? Q that for every point Q, there exists a point P so that f of P equals Q. Okay, this is exactly the same definition regardless of your domain and target of an arbitrary function, but we're just phrasing this in terms of points. Okay? Okay. 3. Of course, I bet you can guess what's coming next. A mapping is 1 to 1. Or equally well, you could say injective. If f of r equal to f of s implies that r is equal to s for any points r and s in the plane. Okay. So, finally, transformation is a mapping which is both onto and 1 to 1.
So it's a bijection.
Yes, thank you. Meaning that it's a bijection. Okay? I'm trying to train myself to kind of stick to the terminology onto and 1 to 1 more often because the book uses that consistently. I'm more prone to say, if you catch me slipping, I'll say injective or surjective. But it's worth saying. I try to tell you all the terminology that you could encounter in any resource. Okay? That is to say, both injective and surjective, which, in other words, is bijective. All bijective means is injective and surjective. Okay? Okay.
So we're just going to use transformation as a bijection from R2 to R2.
That's right. All this boils down to a transformation is just a bijection of the plane onto itself. So, I said the collection of mappings is too big to be interesting. In fact, the collection of transformations is even too big to really be that interesting to study. So, really, because we're interested in Euclidean geometry, going back to this original source of axiomatized geometry, we want to study transformations that behave well with regard to the things that are axiomatized by Euclid, namely lines. Okay? So, the set of all transformations is still too big. To be interesting. So we restrict ourselves more. So, given a transformation, f from R2 to R2, if for any line, which I'll denote by lowercase cursive l, just because it's the easiest thing to see on the board. Just an L looks like a 1 or an I, too confusing. For any line in the plane, we have the image of L under F is also a line. Then we call F a collineation. Okay, so that is to say, not only must we be bijective on points to be a collineation, we must also take lines to lines. Okay, so again, this terminology is potentially confusing. But note here, I wrote L as a subset of R2, not an element, i.e. not a point. So I'm looking at the image of L under F. All too often I've seen students confuse this with, oh, I'm just evaluating a function here. No, you're looking at a set. This is a set. Okay. So, right. Just a couple quick intuitive examples, which we'll come back to and make precise in a couple lectures, maybe tomorrow. All translations are collineations. What's a translation?
Point is moved by an equivalent vector.
Yeah, you just shift everything over, or in any direction that you want. Everything stays in its same relative orientation, and you just slide it whichever way you're translating. Okay, like I said, we'll make this precise in due time. But I think probably everybody has a good intuition of what a translation actually is. Okay. Furthermore, all rotations are lineations. Okay, same type of deal here. You take the plane and you rotate it by some angle. That takes lines to lines, right? Also, yeah, I guess I should say, if you have a line and you translate it by some vector, it remains a line, right? Good. So this is implicit in everything I've said already, but I think it's worth writing down. This, again, I'm trying to be faithful to the book here, because I don't want you to be confused when you read the book, and it's different than what we wrote. Okay, so points are denoted by capital Roman letters, as we saw before with P and Q and R and S when we talked about onto and one-to-one mappings. Lines are lowercase Roman letters. Okay, as we saw here, lowercase l, which you might think is kind of backwards because lines contain points, but somehow points are the primary object of study, and then you think of lines afterward. Convention. I don't know why. I'm sorry. Okay. And also, one more piece of notation. From this point on, transformations are lowercase Greek letters.
Like same with DT and group theory, or like on groups on a triangle or something like that.
I'm sorry, say that again.
It's like same like DT and like groups on a triangle and group theory course.
One more time, I'm sorry.
Like when you have like transformation groups on a triangle and group theory course, like that kind of those kind of group layers.
Yeah. So for example, yeah, you probably saw phi a lot in group theory, or alpha, beta, gamma. For those of you who are not that familiar with the Greek alphabet, I would recommend taking a look at page 2 of the textbook. There's a good list there, and there's some of those that you'll like never see. But in case I ever write a symbol on the board that you don't recognize, please ask me. Or look it up later, or both.
I would be scared to see an Omicron number.
Yeah. Okay. So, right. I've kind of given you an outline of what our goal is, right? We're going to develop this concept of transformation to study Euclidean geometry. And Euclidean geometry, you'll sometimes see as called synthetic geometry. What does that mean exactly? So, should say classical Euclidean geometry is sometimes called synthetic geometry. And if you remember taking geometry in high school,
Couldn't just get started.
because you synthesize things from axioms. You begin with axioms and you deduce consequences of those axioms. You synthesize things from the axioms. Okay, and this is, if you remember taking geometry in high school, this is exactly what you were doing, right? It's like, okay, here's my postulate, down and down the line.
Two column proofs.
Right, so that is the technical term for proof that you remember from high school geometry. Okay, so Euclidean geometry has nothing to do with algebra, right? Well, that's a bit of a misnomer. synthetic geometry does not use algebra, is what I mean to say. Okay? By contrast, the use of algebra to, that is to say, what do I mean by algebra? Specific numbers and computations was introduced by Descartes. In what year? 1637. In his book, this is some ego on this guy. The Geometry. Okay? So, why do I bring this up? Because in our study of transformation geometry, we'll freely switch between these viewpoints of synthetic geometry, and by contrast, this thing introduced by Descartes, sometimes called analytic geometry. All right, why is it called analytic geometry? Anybody know any Greek? What analysis means?
I can split.
Yeah, it means to break things apart.
Right.
Right? And that's what you're doing when you ascribe specific numbers to, say, a point. You're taking away its whole essence.
It's no longer abstract.
It's no
longer abstract.
It's no longer abstract. That's right. You've broken the abstraction and made it into something that's computationally tractable. Good. So, we'll go between these freely. Transformation geometry can be developed in tandem in these perspectives. And we'll do exactly that. But just a couple things I wanted to say about analytic geometry. Okay, so there's some definitions that I think everyone should be comfortable with, but I'm going to say them anyway. Okay, so the Cartesian plane is R2, which now, in the lens of analytic geometry, rather than the set of points capital P, is the set of ordered pairs, x comma y, such that x and y are real numbers. A point in analytic geometry is given by, well, if I want analytic geometry to reflect synthetic geometry, I had better have these abstract P's be equal to ordered pairs, because points are elements of the plane, and what are my elements of the plane here? Ordered pairs. Okay? How about a line in analytic geometry is given by, now remember, L is a set. And it's a set of what? What are the elements of the set L?
Pairs.
They're ordered pairs, yes. They are points in the plane that
You have to obey an equation.
they have to obey an equation. They have to lie on a line specified by a certain equation. Okay? So, that is to say, okay, here's the general equation for a line in the plane. And note here I use capital X for a variable and capital Y, just so you're not confused with the ordered pairs that are satisfying this equation. Okay? So here's the general equation for a line. AX plus BY plus C is equal to 0. Okay, you can manipulate any line to get it in this form. Okay? So, but then I also add this extra condition that not both A and B are 0. Why is that?
That would be the entire plane.
Yeah, well, as long as C is not 0, that produces a...
Either the entire plane or nothing.
Right.
Which is not a line.
Exactly. Yeah, you get a pathology, right? You either have a non-zero constant equal to 0 or a 0, 0. So every ordered pair satisfies that. Okay, so in order to be the true form of what we consider a line to be, we have to have not both A and B are 0. It's okay if one of A and one of B is 0, but not both. Okay, so let's continue with our brief encyclopedia of analytic geometry, right? The distance between 2 points, x1 comma y1 and x2 comma y2, is just given by our old familiar friend, the distance formula. Okay? And finally, this is just a piece of notation. The origin in the Cartesian plane is denoted capital 0, right, which is the ordered pair 0, 0, or capital O, if you like. Okay, so this might seem, again, I understand it might seem like I'm just saying a bunch of things that you already know. But each of these concepts will be important for describing subsets of collineations that we will be interested in studying later. Okay, so I know you know this, but I want to emphasize that it's important. Okay? Good. So here's an interesting side note. The Cartesian plane is the so-called standard For our purposes, we'll identify them. However, there are many other analytic geometrical constructions that satisfy Euclid's axioms for a plane. And you're able to do a version of geometry in these non-standard models. Okay? I find that extremely interesting. For a non-standard model, consider Q squared, the rational numbers. So geometry becomes quite a bit different when you do it analytically, but synthetically, it's the same. Okay? That's a subtle point, and I unfortunately will not be able to stress that very much during our class, but I think it's really interesting. I wanted to let you guys know. So let's do some more in-depth examples than just the intuitive ones I gave you before. Okay? So, the mapping alpha, of course, going from the plane to itself, given by alpha of the ordered pair xy is equal to the ordered pair x squared comma y is not a transformation. Why not?
Doesn't preserve lines.
Well, a transformation doesn't have to preserve lines.
It's not injected.
It's not surjective either. Okay? So, let's just say, since, for example, there's no point x comma y such that alpha of x comma y is equal to, say, -1 comma 2. And we have some point in the plane that is not hit by our mapping alpha. But it fails to be surjective. Okay. That was our first example. Let's take the mapping beta. And I will continue to write this redundantly for at least a little while. Mapping R2 to R2. Given by beta of x comma y is equal to x comma y cubed. Okay, first let me ask, is this a transformation?
Yes.
heard one yes. Does anybody else have any opinions on that? Okay, if you don't, let's talk about it. So this is, in fact, a transformation. Because since the point u, comma, the cubed root of v is the unique point set to u comma v by beta. And that's for any numbers u and v. Okay, so let me just say, check, this is a bijection. That's worth doing by hand yourself. You know, I gave you the abbreviated answer. Check this for yourself as well. Okay? Oh, yes, Samuel also said yes. Good. Now, is V a collineation? No. Okay, why not?
Well, if you look at it as a function, you can see that it's not linear anymore. Or it would, yeah, because it's a linear function.
Okay, I mean, that's the right line of thinking. But to be totally sure, let me ask you to produce a line in the plane which is not preserved by beta. Yeah, good. Just the line through the origin. Y equals x. Right? However, it is not a collineation. Since, let me draw you a picture. Here's a terrible schematic of the line y equals x. I didn't even go through the origin there. Let's just make it really fat. There you go, now it goes through the origin. Okay, so beta, we agreed, is a transformation. So I take the plane and I operate beta on it. And what do I get for the line y equals x?
Cube root of x.
Yeah, exactly. I get that this is taken to the cube root of x. Right, so let's see. Something like that, right? Okay, so in other words, I took a line, operated a transformation on it, and got a cubic equation. No, not a collineation. Okay, I think, you know, it might, at a glance, just going by the definition, it might seem kind of intimidating to be like, oh, well, how do I really tell if something is a collineation or not? But when it fails, usually you can find a line that gets turned into a curve. Right? I mean, there's more pathological things that could happen. But most of the things we look at, you'll be able to see visually. Okay? Let's look at one more example. Example 3. So let's take gamma from R2 to R2. Given by gamma of x comma y equal to negative x plus y over 2 comma x plus 2. I'll just tell you is in fact a collineation. Okay, so who can tell me the steps I need to take to verify this?
I don't know how far to go about it, but I would include your elsewhere for this.
Okay, that's not totally off the mark, but what do we have to do conceptually? What are the things we have to check off to show that this is in fact a collineation? Yeah, first of all, show it's a transformation. And then show that it preserves lines. Take an arbitrary line, stick it into gamma, and see if you get a line out. This is where analytic geometry becomes extremely useful, because we have a constructive equation to describe what lines are. Okay? Okay, so let's show first that it's a transformation. Let's just set u equal to negative x plus y over 2, and v equal to x plus 2. Well, then we can find a unique solution, x and y, for this equation, for this system of equations, sorry. Okay? So, I guess x is equal to v minus 2, which of course implies that y is equal to u plus v minus 2 times 2. I just solved this for y and plugged in v minus 2 for x here. Did some algebra, some rearrangement. Okay. So in other words, 2u plus 2v minus 4 is the unique solution to gamma of x comma y is equal to u comma v. I guess I should say for any numbers, real numbers, u and v. U and v. Right? So basically, u and v can range over anything here. Right? So by finding the solution to this system of equations, I found the unique x and y that spit that out when put into gamma.
And confirm that it's always defined, which means that, yeah.
Yeah. Okay, so altogether, gamma a transformation
So just wondering, so it's a transformation because the x and y variables or the u and v variables are all like to the first power. Is that why we can consider a collineation?
Yeah, so there's a connection here, right? That there's only first powers appearing in some parameterization of the translation.
That's why I thought linear algebra.
Yeah, good observation. And we will talk more about that in a precise fashion soon. yeah, by the time we finish the course, you'll be able to just, most of the time, look and be like, oh, is this a collineation or not? It can be harder than that, but a lot of times you'll be able to just look. Okay? So yeah, let's just go through the formal steps to show that it's a collineation. Okay, so to show a delineation, well, first of all, let's suppose some point x comma y are on a line with the equation ax plus by plus c is equal to 0. Well, I'm going to continue to be pedantic for a little while. Okay? This means that a little x plus b little y plus c is equal to 0. Here I've substituted in the specific values of little x and little y. Okay? So now, I just use the solution that I manufactured to plug in for x and y here. Okay? So what does that give me? That gives me a times v minus 2 plus b times 2u plus 2v minus 4 plus c is equal to 0. Now all I have to do is collect terms to get an equation, a linear equation that v and u satisfy. Okay? So, this is just algebra, by which I mean high school algebra, not abstract algebra. Okay? So what does this give us? This gives us 2b times u plus a plus 2b, oops, 2b, times v plus c minus 4b minus 2a equal to 0. Yeah, I just isolated u and v. And I have coefficients in terms of my original linear coefficients. Okay, the coefficients of my original linear equation. Okay, so this in turn means that u comma v is a point on the line to be capital X plus a plus 2b capital Y plus c minus 4b minus 2a is equal to 0. So in other words, gamma of xy lies on the above line. Okay? So in other words, we took x and y on some line, and then we derived an equation for the line that gamma of x comma y lies on. So we take a line to a line. Okay, so that means it's a collineation. Now, let me give you some problems to do for tomorrow. And then I think we'll adjourn. And never fear, I will put the homework problems on Canvas after class. And for those of you who came in late, remember, homework's not graded. Just work on them as best you can, and we'll do them, at least some of them, together tomorrow. So, textbook. Um, 1.1, 1.2, 1.4, and 1.5. This will give you good practice in identifying different types of mappings. When a mapping is a transformation, when it's a collineation, so on and so forth. And then, yeah, we'll start class tomorrow by just going over enough of these. I'm not going to say that we'll do every single homework problem together, but just enough to make sure everybody has a clear understanding of what's going on. Okay, so any questions before we adjourn for the day? Is the textbook available digitally? As the bond asks. You know, I don't know. In a legal fashion, I don't know.
It's available for rent on Google Play Books.
Okay,
It's like $20 for 90 days.
okay. That still seems like kind of a ripoff. I'm sorry to hear that, but at least it's an option. Yeah. Oh, yeah, so, I don't know, am I saying to do the problems in those sections or just the questions within a specific section? So, there's only 2 sections in chapter 1. In fact, there's only 2 sections in every chapter. And all the exercises are at the end of the chapter. So, 1 point, anything, is just the exercises at the end of chapter 1. Okay? And that it holds for the entirety of the book. It's really just, the first number is the chapter indicator, and then the final section of each chapter is just the exercises. Okay? Great. Yeah, and I'll make that clear in writing on Canvas within a few minutes after we adjourn. Okay? Good. Any other general questions, comments? Is my volume okay? Everybody can see clearly? Will there be exam practices? Yeah, sure. There'll at least be,
Promises.
yeah, there'll be something like a review before. That's fine. No, and don't worry. As each exam approaches, we'll talk about exactly what the expectations will be and how that'll happen. But yeah, there'll be practice material for the exams. Yeah. Okay then. So I'll see you all tomorrow.
Bye. Thank you, Professor.